In today's lecture, we're going to discuss the path dependence of a line integral. So right here I have an integral, the integral of y squared dx plus x dy over c. Now, suppose the only thing I told you was that I wanted to connect -5, -3 to 0, 2. Okay? You can take any path you want from this point to this point. Would it affect the integral? That's the question. Okay? So let's find out. So let's consider two paths. Okay, so C1 path, that's the top one, that's the straight line. Now the straight line, this is not difficult to calculate. You could solve for y, find the slope, and so on. You know how to do this. Path 2, I'm telling you, it's x equals 4 minus y squared. Well, you can check for yourself. One representation for the first curve, so this is C1, one representation is going to be xt equals 4t minus 5, yt equals 5t minus 3. Again, you don't have to use this particular parameterization for the straight line. You could actually solve for y, say y equals mx plus b, right? Solve for m, solve for b, and then let x equal t, so that x equals t, and then y equals mt plus b. You could do that, but I'm just going to tell you, okay, this will work. So let's compare these integrals. The first one, when I evaluate it, it's going to become the following. Okay, so how did I get this? Well, in the previous section, when I had x equals 5t minus 5, y equals 5t minus 3, I guess I technically forgot to say, and t goes from 0 to 1. So let me just say that right now. So t is going from 0 to 1. Here I replaced y with its form in t. And how did I get this right here? Well, remember, when I do this sort of integral, right, this is going to have my function f, and then it's going to be dx dt, right? So this 5 dt, that's just the derivative of the x, right? So here's x, 5t minus 5. The derivative of that with respect to t is 5. And so this is where the 5 dt comes from. So just, if that doesn't make sense, focus on this equation and then stick that in right there. Okay, so once I carry this calculation out, I'm going to arrive at this, 25t squared minus 25t plus 4 dt, and this is going to equal -5/6. Okay, good. On the other hand, if that's a C1, C2 is the following. Okay, so you get 40 and 5/6. Okay, so how did I get that? Well, remember, C2 was, by definition, x equals 4 minus t squared. And I said, let y equal t. Okay, so whenever I see, oh, sorry. Well, it's a dummy variable, so it doesn't matter if you call it t or y, but this is how I want to teach you. The book is going to use y. If you go to your book, this is on page 1119, example 16.2.4. But I want to use t because this is how we did it in the first example, okay? Or the first half of the example. So I take my y, and I'm going to put down t. Right, so here's a y, I replaced it with a t, so I get t squared. Dx, this is going to be the derivative of this, which is negative 2t. This is negative 2t, okay? And then over here I have x, right? X is 4 minus 2, and dy, again, is dt. So that's all very straightforward. When I get my final evaluation, I see I get 40 plus 5/6, which is clearly not negative 5/6, so the two are not equal. So this is just to illustrate that, in fact, the path between 2 points does affect your integral. See you in the next video.